Greetings, everybody. Let's take a minute to look at the problem type of limits of the form 0 over 0. Okay, with this being my example. Okay, so here goes. First of all, if I'm given this limit, initially I might think, well, there are lots of ways I could do this. Maybe I could somehow generate a graph and look at the graph, do it that way. Another technique we've seen is to make a table. But in this video with this kind of problem, I have a unique technique. Okay, so first of all, I call this limit being of the form 0 over 0 for this reason. Here's what happens to this function, x squared minus 1 over x plus 1, if you let x be negative 1. Okay, I know the limit says as x approaches negative 1, but let's just look at what happens if x is negative 1. Okay, so if x is negative 1, I put it in for x, and it looks like this. I get negative 1 squared on top, that's 1, minus 1 is 0 on top, and then I get negative 1 plus 1 on the bottom, and that's also 0. So if you were to let x be negative 1, that's what this is going to give you. Okay, that's why I say it has this form 0 over 0. Now, whenever you encounter that, here's what we'll do. We'll algebraically reduce the function that we're given. In this case, that's x squared minus 1 over x plus 1. And then once we algebraically reduce it, I'll let x be negative 1 in the reduced function. That's the general technique. Okay. Now, we might see other problems that take the same form, 0 over 0. In this technique will still apply, but the problems might initially look much different. And the step of reducing it might also look a little bit different. Okay, so those will be covered in other videos, but just right now, like sneak peek into what the other problems might look like. Here's another one that takes that same form. See, it says, what's the limit as h goes to 0? Well, what if h was 0? What would this be? On top, I would get 3/5 minus 3/5. That's 0 on top. And on the bottom, I would get 0 there too. So that would be 0 over 0. So same type of problem, same technique, but this first step of reducing it might look a little bit different. Okay. All right. Now, so let's not get too spread out with all this. How would we do this one? How would we algebraically reduce it, given that it has this problem type of 0 over 0, and the first step is to reduce that function that we have. Okay. All right. So let's see. It would look like this. So if I was going to algebraically reduce x squared minus 1 over x plus 1, I think the obvious and apparent technique is to factor and cancel. That x squared minus 1 on top, that is something that can be factored. It's called the difference of two squares. It factors as x plus 1 times x minus 1. If I do that, then I'm looking at x plus 1 times x minus 1 over x plus 1. And then we can cancel the x plus 1s because they're identical. And then that would give me x minus 1. Okay, so that's the reduced function. It's like I had x squared minus 1 over x plus 1. That's what I appeared to be working with when I started. But upon reducing it, it's just x minus 1. Now I'll let x be negative 1, which is this limiting value of the x in that reduced function. And I get negative 1 minus 1 equals negative 2. And then we're done at that point. Our conclusion, the limit as x goes to negative 1 of x squared minus 1 over x plus 1 is negative 2. So do you see how these answers have panned out according to my work? Okay, so here's the question as we might see it in the assignment. First, it says simplify the given limit. All right, that's that first step, right? I told you we're going to reduce that function that's given. All right, that function reduces to x minus 1. So it's like they're saying, well, doing this limit is the same as doing this much simpler one. Okay, that's what our basic conclusion was in the first step. And then the second step is just to evaluate that limit as we did, and then you see the answer that we got there. All right, so that's how it's done. Look at it like this. You look at the limit, you notice that it's of the form 0 over 0. From there, you know the technique is to reduce the function that you're given, and then let x be whatever that limiting value is. Okay? All right, now, that's the same technique that I would use for this one. except for the algebraically reducing step is a little more complicated. It's more involved, but we can look at it in other videos. Okay. All right. So that's how you do this one. Now, I think it deserves some follow-up questions now that I showed you how to work it. Okay. So I want you to consider, and hopefully at the end of the video, I want you to understand what's happening here. Okay. The short answer is that this function right here that we're given with to start in order to do this limit has a hole in the graph at -1. Okay. And that's all because when you have this function and you let x be -1, if you calculate f of -1, you get 0/0. That right there is an indicator that there's a hole in its graph at x equals -1. Every other point is okay. Every other point is there. We got this solid graph, complete in every aspect, except for at this one spot where x equals -1, where there is a hole. Okay, so that's the short answer. We can now associate, if we want to, as far as graphs go, and sometimes we need to look at graphs, that 0/0 tells me that there's a hole in the graph at that spot. Okay, now that's the short answer. Now we need to consider the long answer. I'm going to go into a little more detail here. It turns out that, you see this function right here? It's like they're saying we can do this limit or we can do this much simpler limit, because this function can reduce down to that one. That's what it looks like, okay? And there's some truth to that, but it's a little more complicated. All right, here's the truth. F of x equals x minus 1 only if x isn't -1. So that function that I was given to start with is actually the same as x minus 1, but only if the x is not -1. Then they're not the same, okay? And f of x, this function I started with, is undefined if x is -1. Because obviously you can't, what if you put -1 to that function? What do you get? You don't get anything. You get 0/0, which doesn't give us any return value. Okay? So, all right, now the explanation on this. Here's the function I started with. This is what I did over there when I reduced it. I started with this function, I factored it, and I canceled, and I got to that one. But can you really do that? I mean, we take that for granted. When you took algebra, you probably did canceling all the time. But there's some fine print to it that you may not have ever learned. Okay? Can we cancel x plus 1 over x plus 1? I mean, we're doing math here, and math is done with numbers. Once we get to algebra and beyond, we start using variables when the numbers aren't known. So here I have some variables. I've got x plus 1 over x plus 1. But the x has to be a number. Okay? We're canceling numbers there. And we can only cancel under the condition that that x is not equal to -1. Why is that? If x was equal to -1, then this x plus 1 over x plus 1 that we were trying to cancel would take the form of 0/0. And we can't cancel 0/0. I mean, imagine you just had numbers, and that was 4 times -2 over 4. You cancel the 4's, and you get -2. But given that under this one condition, this one and only case that the x is -1, that turns out to be 0/0. We can't cancel in that case. So that's why I would say that the function we started with does reduce to this one, but only under the condition that we're not canceling a 0/0, which would happen if the x was -1. Okay, so all right, so we'll say this. We'll say our function reduces to the simpler one if x isn't -1, and it's undefined otherwise. So here's what that means. The graph of this function is the same as the line x equals x minus 1, f of x equals x minus 1, which you see here, only if x is not -1. So it's like I've got to graph all the points on this line, leaving out the one that would be there if x was -1. What would that point be? Well, if I were to put -1 into this, I would get -2. So that's where the hole in the graph is. Okay? The hole in the graph is at that x value that would give me 0 over 0. All right. And it's undefined at -1. Yes, if you put -1 in, you get it's 0 over 0. It's undefined. You don't get a return. There's a hole. There's a missing point in the graph. So on. So that's the long answer to why this has a hole in the graph at -1. Okay, we'd be having some kind of nonsense canceling at that point. All right, now how does that relate to the limit? Well, if I was going to do this limit, I said, what's the limit as x goes to -1 for this function? And I knew the graph was this. It was just a line in it with a hole at -1. Then I could look at that graph and say, well, if x is near -1, that does put the y's near -2 down there. I see why the limit turned out to be -2. There might be nothing at -1, but the limit is asking us what happens when x is close to -1. Look at the graph, we can see when x is close to -1, y is close to -2. So that's another way to see our limit. All right, quick summary. If we have limits of the form 0 over 0, we'll algebraically reduce the function, then evaluate the limit from there. In cases like that, there's a hole in the graph at some point, the point where the function is 0 over 0. And it's all because when we did that step of reducing, we can't actually do the canceling step if what we're canceling turned out to be 0 over 0, which would happen at that initial limiting value that we saw.